We are continuing our look at section 3.5, rational functions and their graphs. Let's take a look at the definition of a horizontal asymptote. This is a line, a horizontal line, y equal b. So remember, horizontal lines are lines where all points on the line have the same y coordinate. Therefore, the equation only needs to give you that value of y. X can be any number as long as y is this fixed value b. Then that point will lie on the horizontal line. So the line y equal b is a horizontal asymptote of the graph of a function f if f of x approaches b as x increases or decreases without bound. So when you are looking at a horizontal asymptote, x has to either be increasing without bound, as we see x doing here. So for x to increase without bound means x goes to infinity. So x gets larger and larger and larger and larger. This is an indefinite movement to the right. Remember, that's what x going to infinity means. I'm moving indefinitely to the right. If you have a horizontal asymptote, as x moves indefinitely to the right, that means as x goes to infinity, your y, your f of x, will move to a constant value b. And remember, the line y equal b is the line which is horizontal, which means all the points on that line have the same y coordinate. The x's change, but the y's do not. So here, y is approaching b from below. So these y values are getting closer and closer to b, but they're always slightly smaller than b. Here, the y values, f of x values, are approaching b from above. So these y values are always slightly bigger than the value of b as x goes to infinity. And then for a horizontal asymptote, this is not true for a vertical asymptote. For a horizontal asymptote, the function can actually touch the horizontal asymptote at some point. Now notice in the first two pictures or graphs, the function does not touch the horizontal asymptote. It gets infinitesimally closer and closer, but never actually touches it. Here in this third graph, we see there's actually a point where the graph touches the horizontal asymptote. This is something that can happen. So the function at some value of x actually equals b. Now notice though, as x goes to infinity, as we move indefinitely to the right, the function approaches the horizontal asymptote. However, in this case, there was some earlier value of x that actually equaled b. Here the function is approaching b, and again this approach is from below. The y values or function values are getting closer and closer and closer to b as the x's increase without bound. It also is important to note, as the definition says, that x can also be decreasing without bound. Now in the three pictures that are shown here, x is increasing without bound. But it is possible to have a horizontal asymptote, as we showed in an earlier example, um, when the function is when the x value is decreasing without bound, the function can also be approaching the horizontal asymptote. We don't have a picture of that in these three examples, though. But if we look back at this earlier example where we were talking about the arrow notation, we see that as x decreases without bound, remember that's the same as saying x goes to negative infinity. That's also the same as saying we are moving indefinitely to the left. Remember in this example, as x went to negative infinity, the function was approaching 0 from below. And so this is an example of a horizontal asymptote where y is equal to 0, where the x is decreasing without bound. So when I have a horizontal asymptote, as I have here in this picture, x can be decreasing without bound, or as we see here, x can be increasing without bound. And that's what's happening here. And the horizontal asymptote here is also the x-axis, whose equation is y equal to 0. Here, though, we are approaching, the function is approaching the horizontal asymptote from above on this branch of the graph. Here, the function is approaching the horizontal asymptote y equals 0 from below. So ultimately, when I want to locate horizontal asymptotes, I have the following that can happen. F is a rational function. So f of x is equal to some polynomial function p of x, which is in the numerator, over another polynomial function q of x, which is in the denominator. And we know that the leading coefficients of what we see here, a sub n and b sub m, as in Mary, cannot be 0. So the degree of the numerator in the polynomial shown is n, as in Nancy, and the degree of the polynomial in the denominator is m, as in Mary. So three things can happen. Either the polynomial in the numerator has a degree n that is less than the degree of the polynomial in the denominator. So either n is less than m, Nancy is less than Mary. If that occurs, then the x-axis, whose equation is y equals 0, is the horizontal asymptote of the graph of f. If Nancy equals Mary, n equals m, the line y equal a sub n, a sub Nancy, over b sub m, b sub Mary, is the horizontal asymptote of the graph of f. If Nancy is bigger than Mary, n is bigger than m, the graph of f has no horizontal asymptote. So those are the three things that can happen. Either the x-axis is the horizontal asymptote, or some other horizontal line is the horizontal asymptote, or the graph of f has no horizontal asymptote. So you'll have one of those three situations in your rational function.